So in this video, we're finally going to define voltage and current so we can begin to talk about electrical signals and how they behave. So we'll define voltage and current. It's pretty easy. We're not going to use too much physics here. It's going to be very intuitive, I hope. We'll then talk about the circuit elements. These are elements that act on voltage and current in very particular ways, and these are used to construct real live analog circuits. So what are voltage and current? So voltage is also called electric potential, and it provides the push for the flow of charged particles. So the idea is that you have a region of positive to negative voltage, and the positive part is supposed to represent that it has a higher potential, electrical potential, than the negative side. So this is downhill, if you will. Higher potential where it's positive, lower potential where it's negative. And so generally, if you just had a charged particle, a positively charged particle, it would want to go downhill. That's what a voltage does. It provides the push. Voltage has units of volts, usually indicated by a lowercase v, sometimes an uppercase v, named for Alexander Volta, the Italian physicist who discovered the battery, by the way. Current is the flow of positively charged particles in the direction that's indicated. So what this means here is that there's a river of charged particles flowing this way. Notice the word current is analogous to the flow of water in a stream or a river. And the current is flowing this way. So the interesting thing, though, is that this is the flow of positively charged particles. If you had negatively charged particles, like an electron flowing in this way, it turns out positive current to the right means the electrons are flowing to the left. You can blame this convention of giving a negative charge assigned to the electron to Benjamin Franklin. As you probably know, it's the electron. It's the workhorse in electricity, and we talk about current here as a flow of positively charged particles, but the electrons are actually flowing the other way, but we don't really care. We talk about what's the actual value of the current that we have. The unit of current was named for the physicist Ampere, usually denoted by a capital A. 1 volt is not a very big voltage. I'm going to show you some batteries in a second, and they're typically 1.5 volts. 1 ampere of current, though, is a lot of current. Typically, in most circuits, you can range from the microamp range to the milliamp range. 1 ampere occurs in things that are coming out of the wall, for example. You can supply a lot of current out of a power socket. Now, how the charged particles actually flow in response to an applied voltage depends on the conducting medium. We're going to go through several circuit elements in R, and the laws of physics determine how the voltage and current are related to each other. So it's not always true that if you have a positive voltage, like I've indicated over here, that the electrons the positively charged particles always flow that way. That's not true. It depends on what's in between, and we'll see that in just a second. So let's define a convention here. So here we have a generic circuit element. Don't know in detail what it is, but there's a very important convention here. And that is, if you define voltage to be plus to minus that way, you want to define positive current as going in the positive side of the voltage. This is a convention that's extremely important to follow while we're getting used to circuits and how to think about them. This does not mean that the voltage V is going to wind up being a positive number. The way you assign voltage is up to you. It could turn out that once you put it in the circuit and figure out how it works, the voltage is negative. And it could, of course, turn out that the current is negative too. But in order to define what we call the VI relations, the relationship between voltage and current that a given circuit element imposes We must go by this convention. So let's talk about some rather simple circuit elements first. The first is just a wire. So notice the word here, ideal. This is an ideal wire. So an ideal wire lets any current flow that the circuit wants to flow with no voltage drop. The voltage is zero. Current is essentially pushed through here with no electric potential being required. This is an ideal wire. This is in fact what a superconductor is. It allows current flow with no voltage to be applied, no voltage drop. A real wire has a small resistance and does not behave like this at all, but this is what we use in circuits. This is a model of an ideal circuit element, we call the short circuit, that lets any current go at all, but the voltage drop is zero. And you might guess that there's also an open circuit, which is what I call a dead wire, which in this case there's no current flowing because it's open, it's free space, if you will, in between, but there is a voltage drop. And the voltage drop can be anything that the circuit in which this open circuit is found can occur. So the important point here is that in an open circuit there is no current flow through the open area. I equals zero. Okay, well, let's talk about something that actually does something. Perhaps the simplest circuit element is the resistor. And here, voltage and current are proportional to one another, and the constant of proportionality is the resistance R. So 1 ohm is a volt divided by 1 ampere. 1 volt divided by 1 ampere is 1 ohm, and the symbol for an ohm is a capital omega. So very simple circuit element, as we'll see when I show you some real ones in just a second. The capacitor is a bit more interesting. The symbol for a capacitor is this set of lines going into what looks like two perpendicular lines. The VI relationship is that the current is proportional to the derivative of voltage. And that constant proportionality is the capacitance, which is measured in farads. Farads is named for Michael Faraday, the very important 19th century experimental physicist. Now, how do you build a capacitor? Well, it turns out the symbol for the capacitor gives it away. If you had two parallel plates and you put leads to them and applied a voltage to it, or put it in a circuit, what's happened is that charge wants to accumulate on this plate, and the current actually doesn't flow through, it doesn't jump across those plates, but current can slosh back and forth as if it were flowing through the circuit element. And it turns out the capacitance C is equal to the dielectric constant of the medium that's in between times the area of the plates divided by the distance between them. So in order to get the capacitance up, you have to have a big area and or a very small distance between the two plates. Now, to give you an idea about scale here, a 1 farad capacitor is huge, it's gigantic, as the way the units all work out. Typically, capacitors are in the millifarad. That's a pretty big capacitor. Even microfarads, even nanofarads, and even picofarad capacitors are found in lots and lots of circuits. But that's the way they're constructed out of parallel plates. This goes back to what I said about the nature of the medium for the circuit element defines the VI relationship. Resistor is probably the simplest medium. The capacitor is an interesting medium too, but has a bit more complicated VI relation. And then finally, there's the inductor. Inductors are, the symbol here for an inductor is supposed to resemble a coil of wire, has an inductance L, which is measured in henries, and for Joseph Henry, an American 19th century physicist. And it has the VI relationship, the voltage is proportional to the derivative of current. In some sense, it's the opposite of a capacitor. And if you use the laws of physics to figure out how voltage and current are related when there's a coil of wire, you'll discover that to a good approximation, the voltage is proportional to the derivative of the current. So inductors are found, for example, in automobiles. When you talk about the coil in an automobile, it turns out it's a big inductor. Okay, so let me show you some resistors. So here's a photograph I took of a set of resistors I happen to have. I want you to notice, first of all, they're all the same size, no matter how big the resistance is. So this is the actual resistance of each of these circuit elements, resistors rather, going all the way from 10 ohms to 1 megohm. I want to hold up a resistor to give you an idea of the size. This happens to be the 1 megohm resistor that I showed you in the photograph here, and you can see it's pretty small. The size of the resistor determines how much power it can dissipate. These turn out to be 1/4 watt resistors, and we'll talk about the power considerations in a second. Well, how did I know that these are the values of the resistors? And I don't know if you can see it very well, but there are little bands of color going around each of the elements, and it turns out that brown, black, orange is a 10,000 ohm resistor. And this brown, black, red here turns out to be a 1 kilo ohm resistor. So I'm reading those colors from the top. This is called the color code, and you can go online and Google color code, and you'll find lots of calculators, what are called calculators for color codes. You type in the colors and they'll tell you what the resistance is, or you can type in the resistance and they'll tell you what the colors are. And you should remember them as you get deeper into electrical engineering. But the important thing here is size does not determine the resistance. What determines the size of a resistor is how much power it dissipates. And I'm showing that in the next slide, where I have a much bigger resistor. So here's that resistor, and you can see it's quite much bigger than the other resistors I had. And if you look at it very carefully, you can see it says it's 75 ohms, and I don't know if you can see it very well, but down below what I just wrote over, it says it's 25 watts. So this will dissipate lots of power. It turns out it's hollow inside, and that's there to allow more power to dissipate from this. So this is able to put out lots of power. I'm sure you've seen light bulbs. In the US there's 60-watt light bulbs, and they can get very warm very quickly. You can imagine the 25 watts can also get pretty warm. These 1/4 watt resistors don't get warm at all. So let me show you a capacitor. And you can see on the left there a 470 microfarad capacitor, and it's pretty big. There it is. It's pretty good size, bigger than my finger in diameter. And that's, like I said, a pretty hefty size resistor. On the right is a 1 nanofarad resistor, 1 nanofarad capacitor, what am I saying? A 1 nanofarad capacitor, and it's small by comparison, and you'll find that size capacitor in lots of electronic circuits. Finally, let me show you an inductor. And here's the inductor that's in that photograph. It's about finger-sized. And if you look at it carefully, it is a coil of wire coiled around a circular object. And I want to point out something. If you look very carefully at this figure, you can see that the wires coming out look to be silverish. They're not really silver, but they look silverish, whereas they look to be brownish around the coil. And it turns out the brown does not indicate that they're copper. That brownish substance turns out to be an insulator, because if this wire was not insulated, right over here, for example, the wires are touching each other and it would short out the entire inductor. Because they're insulated, this coil of wire now looks like an inductor. And you'll find this, it applies very consistently throughout electrical engineering, that when you tend to see that kind of color, it's indicating that it's a insulated wire. You can scrape it off if you want to get rid of the insulation. Also, as you know, there's a plastic kind of insulation on lots of wires too. But in this special case, I wanted to indicate that this is a very small diameter kind of insulator too. Okay, let's go back and look at the circuit elements again, because there are times when you want to write the VI relations the other way, if you will. So instead of V equals RI, you might want to write I equals 1 over R times V. Well, we call 1 over R is called the conductance. It's given the symbol G, and G is measured in Siemens, named for the German inventor of and designer of telegraph systems in the early part of the 19th century. So the symbol G is for Siemens. There are going to be lots of times when it's more convenient to think about a resistor in terms of its conductance, reciprocal ohms, Siemens, than it is in terms of its resistance. We'll find that out very soon. Now, of course, for the capacitor and the inductor, those derivative relationships turn into integral relationships. And as I said, all integrals in this course are definite integrals, and they all start at minus infinity. So, in some sense, a voltage in a capacitor has infinite memory of all the previous values of the current. All previous values of the current, no matter how they arose, going back to the beginning of the Big Bang, are summarized by the voltage. Of course, there are a lot of different current patterns that will result in the same voltage. Same thing for the inductor. It's the current that contains a memory of everything, all the voltage values that voltage that the inductor has had across it. Kind of interesting that they have this kind of infinite memory, but that's what you get when you have a derivative relationship. Turn it around, it becomes an integral. Okay, let's talk about some different elements, namely sources. And these provide voltage or current to a circuit that we build. So a voltage source is indicated by a circle with a plus to minus indicating the positive direction for the applied voltage V sub S, S for source. So the VI relationship, again, I'm defining my own voltage V and my own current I going in the top in a consistent way, is that the voltage is going to equal whatever the source is for all I. So what this means is that the voltage source puts no constraints at all on the current. It can supply any current that the circuit to which this voltage source is attached will want. What it does is it provides a voltage for all time, whatever V sub S is. Similar thing for a current source is that this will provide a current no matter what the voltage is. Voltage could be 0, minus 100, 10 to the minus 6, really doesn't matter. It's going to provide a given current. Now, notice the little minus sign here, and that is because on this, the way I've drawn it, I sub S is a positive current flowing that way, and we always want I defining the VI relation to go in the positive side of voltage. So these two currents are going the opposite way, and that's the reason for that minus sign. It's just a minor little thing. You just want to make sure you're consistent in the way you define things. But let me point out, it is very, very important that if you define voltage that way, you define current going in the positive side of voltage. Very, very important. Well, let's look at some batteries. So, batteries are a special case of a voltage source that produce constant voltages. And I've got 4 batteries in this photograph. This is a D cell, which is, as you know, pretty big. Gives you a size of scale. If you read the label very carefully, it says 1.5 volts. The little button at the top is the positive side. It doesn't, in most cases, they don't label the negative side. Once you know what's positive, the other end is negative. This is a AAA battery, and if you look very carefully right there, it says it's also 1.5 volts. So again, the size of the battery does not determine the size of the voltage it produces. What it does tell you is how long each battery will provide that voltage. Basically, the bigger the battery, the more oomph, as I like to think about it, the more oomph it possesses, it can last longer. The chemical reactions can be sustained. So a AAA battery in general in a circuit won't last as long as a D-size battery attached to the same circuit. Wanted to point out, I discovered this the other day. This is a battery that goes into my remote control for my door lock on my car. And if you look at it very carefully, right there it says 12 volts. So this actually provides a bigger voltage than a AAA, than a D cell, but it doesn't provide much current. By the way, the 27A that you may see at the top of this battery is a model number. It does not mean it provides 27 amps. I guarantee you it doesn't. And finally, this rectangular battery, you see, is clearly labeled 9 volts. And on the side, you can look to see which end is positive and which end is negative. That's labeled on the side of the battery. Okay, you can buy these clearly at any store. Readily available. So don't forget that when you buy a battery like this, it's open circuited. There's nothing attached to between the top and the bottom. There's nothing there. So if we're here, the way they're pictured, the current is 0 because there's nothing attached to it. These batteries are quite happy to produce 1.5 volts for these two at least, no matter what, because they're just sitting there. Now, how about a current source? Well, a current source will provide a current no matter what voltage is across it. Providing a current means there's flow of charged particles going out of this device. If it's open circuited, where are these charged particles, electrons, going? Where do they go? If it's really open, the current source has a real problem. It has no place for the current to go. Remember, an open circuit does not allow any current, so it's inconsistent. So it's very hard to go to a store and buy yourself a current source that's sitting there like this. It would be perfectly happy if the current source were short-circuited. Now, you could buy one of those, but heaven forbid if you tried to break that wire off to attach it to something, because then it would not be very happy. So current sources are hard to buy in one sense. And you go back to the voltage source. So a voltage source is very happy to be open circuited, but it does not like to be short circuited. So this means the current flows no matter what. Well, a short circuit is a zero-valued resistor. So this means that the voltage, in order for B equal to Ri, for to have a positive voltage, let's say, provided by the source, and resistance is whatever it is, it's 0 for a short circuit. Well, to get a number here, this current would have to be infinite to make everything work out. And so voltage sources do not want to be short-circuited. Current sources do not want to be open-circuited. Voltage sources do not want to be short-circuited. Fundamentals of electrical engineering. Okay. Well, let's talk about power and energy. Now, the conservation of energy principle is that the sum of energies consumed or produced in a closed system is a constant. So you can't produce energy from nothing. A closed system means there's nothing going in or out of this system, and whatever energy is inside that closed system is going to be constant for all time. So what is power? Power is the rate of change of energy with time. So that's just a definition. So P is usually measured in watts, and to be consistent with this definition, the energy would be in joules and time would be in second. So a watt is a joules per second. But the important thing for here is that the power, the conservation of energy principle, that the energy is a constant, means that in a closed system, the power, total power in that system is 0 at all times. Inside that closed system, there could be parts of it that are producing energy, producing power, but other parts have to consume it. They have to consume that power. So we should look in circuits, and what I'm going to show a little bit later is that this law is obeyed by circuits. Whatever is producing the power is also consuming it somewhere else. That's just the way things have to be. Well, what's the definition of power for a circuit? So, definition: the instantaneous power, the power at time t, that is dissipated by a circuit element, is the voltage times the current at those same times. Now notice the word dissipated. So positive power, if P is greater than 0, that means you're dissipating power. If P of T is less than 0, that means it's producing power. And that's the convention, that's the way you think about it. Go back to the derivative convention for relationship between power and energy. So if power is positive, that means the energy being consumed by the whatever element's going up, so it's consuming. But if it's less than, it's producing. So it's all very consistent. What's interesting is that watts is equal to volts times amperes. So you measure the voltage in volts, the current in amperes, multiply them together, and you'll get the power being dissipated or produced by that circuit element at that time. So let's go through the various elements and see what the power equations are for them. So for a resistor, well, V equals Ri. You can substitute this into the power formula up here any way you want. And what you get is that the power is either Ri squared or V squared over R, whichever way you want to think about it in terms of voltage or the current. So, one thing to point out, squaring always gives a non-zero, a positive quantity. Cannot be negative. And that means resistors always dissipate power. And that's why the wattage of a resistor is very important to consider, because it's going to dissipate power, and you better have a physical design for a resistor so it can let the power dissipate freely up to its stated rating, but always dissipate. So resistors dissipate power. So there has to be some other element in the circuit that produces the power that the resistors dissipate. If you look at the capacitor and the inductor, things are a bit more interesting. So I plugged, let's say, the derivative relationship in here and did a little manipulation to show you that the power consumed by a capacitor is related to the derivative of the square of the voltage. So, now the square of a voltage, of course, again, is a positive number. However, its derivative can be both positive and negative. So there are times when a capacitor can actually produce energy, produce power, and there are times when it consumes it. It depends on the nature of V. And the same thing for an inductor. And in fact, the way we think about these are energy storage devices, the inductor and the capacitor. And a capacitor energy is stored in the voltage, and in an inductor, it's stored in the current. These are results, these equations tell you how to calculate the power that's consumed or produced by these various elements. Now, I want to show you how we're going to start thinking about these. So, our fundamental circuit elements are going to be the resistor, the capacitor, and the inductor. We'll use voltage sources a lot. Now, we are going to build systems out of these elements. It's called a circuit. Now, so all of these elements will go into our system. The sources, they're the ones that provide the signal for the input to the system, and will somehow grab a voltage or a current to be the output of the system. So the sources provide the input X. We're going to have to figure out how you build systems out of resistors, inductors, and capacitors in order to accomplish some goal, some relationship between X and Y that you want, and then some voltage or current will be the output. That's what's coming next. We'll try to build real circuits and try to do something useful with them.